Right. So, so one of the biggest struggles, the biggest challenges of this chapter is there's a lot of different methods just to get to an answer, right? So that's kind of why I made this third day, even though there's nothing new in it. I wanted to give you another day just to sort out how do I tell what I'm supposed to do, okay? Because again, I know that's one of the biggest challenges. There's so many different things. Sometimes you make a Venn diagram. Sometimes you make a tree diagram. Sometimes you use one of these four formulas. There's just a lot going on. Okay, so again, let's take another day, just sort through which strategies are appropriate for which types of questions. So here, a player serving in tennis has two chances to serve into play. If the first serve goes out of bounds, the player serves again. If the second serve is also out, the player loses the point. Here are the probabilities based on 4 years of the Wimbledon Championship. So here hi, thank you. So here they break down all the different probabilities. And then the question is, what is the probability that the serving player wins the point? Now, again, lots of information, okay? Just looking at this setup, we're talking about taking a first serve, then seeing what would happen on a second serve. What would be a good way to organize this information? What? I'd say a tree would be better because we have sequential things happening, right? We have to serve first, something's going to happen, and then maybe we have to serve again, and something's going to happen, right? So I actually think a tree diagram would be a really good way to model this information. All right. So on the first serve, it can either be in or out, right? Isn't that really what can happen? So the probability that the first serve goes in is 0.59. The probability it goes out would therefore be 0.41. Yeah. All right. Now, probability that they get the point given that it went in the first time. So wouldn't that be over here, right? So given that we know it went in, what's the probability that they win the point? Or isn't the other option then it's just over, right? If it goes in and they don't get the point, aren't they done for that turn, right? Right? Tennis, yeah? Okay. So if it's 0.73, that if it goes in, they get the point. What's the probability it goes in, but they don't end up getting that point? 0.27. Beautiful. Well, now if it went out, remember, if it went out, don't they get a second chance, right? So now they get a second chance to have it go in or out for a second serve. Okay, isn't that what this is telling us? Given that the first serve was out, what's the probability the second serve is in? Well, it tells us 0.86, right? Which again, what would the complement of that be? Well, what would be right here? 0.14. In this case, if it goes out here, they're done, right? Isn't that another thing? If it goes out twice, they don't get another chance, it's over. But there is one more thing that can happen, right? If it goes out the first time, goes in, they still have a chance to win the point, don't they? Isn't that what this probability is telling us? The 0.59. And again, if it goes out, or if they don't win the point, again, end game, right? They don't get another shot that turn. So before I keep going, is everybody with me on how this flowchart works? Or sorry, how this tree diagram works? I know it's a little bit more confusing to make. But now let's talk about the probability that the serving player gets the point. Okay. How many ways can they end up getting the point ultimately? I see two ways they can get the point. All right. They can get the point here, or they can get the point here. All right. To find any outcome in the end, what do we do with our branches? We multiply, all right? So to find this probability of winning, it goes in and they win. Well, I just multiply 0.59 times 0.73. Again, to find out this way of winning, it went out, then in, then they ended up winning. Don't I have to multiply all three of those numbers? 0.41 times 0.86 times 0.59 to get 0.208034. And again, we talked about there's two ways of winning. This could happen or this could happen. Okay? Hearing that word or tells us what do we do now to find the overall probability of winning? We add them. Okay? So now to finish this up, I'm going to take 0.4307, add 0.208034. And again, there's no technical number of decimals you need to round to. You'll often see me go to 4 decimals in my final answer, simply because that's typically what they show in their keys. But again, there's no firm rules. If you only went to 3, that's fine. It's not like you'll get docked for that. All right, any questions on that one for me? On why that's the strategy we use, anything like that? All right. Then our next one. The Census Bureau says that the 10 most common names in the United States are in order: Smith, Johnson, Williams, Brown, Jones, Miller, Davis, Garcia, Rodriguez, and Wilson. These names account for 9.6% of all U.S. residents. Out of curiosity, you look at the authors of the textbooks in your current courses. There's 9 authors in all. Would you be surprised if none of the names of these authors were among the 10 most common? Assume authors' names are independent and follow the same probability distribution as names of all residents. All right, so let's talk about a couple of things here, okay? So we're looking at 9 authors, right? We have 9 books. We're looking at 9 of the authors. And we're wondering what does it look like, or what's the probability if none of them are in the 10 most common. Okay? So let's think about this. For one of them to be not common or not on the list, what would that look like? If 9.6% of anyone is in those 10, what would it look like to not be part of that 10? Yeah, wouldn't it just be the opposite of that, right? So here, if 9.6% of all names are those top 10, for someone to not be on that list would be 90.904, right? Is everyone with me? But I'm looking at 9 authors. So I want this author and this author and this author and this author, so on and so forth. I want none of them to be on that list. So I have 9 names that I want to not be on that list. What do I do if I have those 9 names? To the 9th power. I mean, you could multiply it by itself 9 times, but that sounds like a lot more work, doesn't it? All right, so let's calculate this. So 0.904 to the 9th power, 0.4032. So did the question actually ask for that number, though? Is that technically what it wanted? No, technically, what does it want? Would you be surprised? Well, according to our calculation, it looks like there's about a 40% chance of that happening. Would it be that surprising to take 9 books and have the authors none of the authors on that list? Would it be honestly that surprising? Not really. There's a 40% chance of that happening. So I'd say here, based on our calculation, we wouldn't be surprised if none of the 9 authors were on that list, because again, there's roughly a 40% chance of that happening. And again, that's nowhere near surprising enough to doubt that claim or anything like that. So I'm not going to write it out, but you guys, to fully answer it, should write a little snippet about not being surprised. All right. Internet sites often vanish or move so that references to them can't be followed. In fact, 13% of internet sites referenced in major scientific journals are lost within 2 years after publication. If a paper contains 7 internet references, what's the probability that at least one of them won't work 2 years later? All right. So here again, we need to think of a strategy. Okay, what would we do here? Well, what's the key phrase that's kind of jumping out at you? At least one. All right. Again, this is a very common thing to pop up on the AP exam. Okay. At least one. Now that sounds challenging to calculate, doesn't it? What sounds easier to calculate? Yeah, what's the probability of none of them not working? Okay, again, doesn't that sound easier? None sounds easier than at least one to calculate. So here we're talking about there's a 13% chance of it being lost. So what's the probability that it's not lost? 87. All right, so there's an 87% chance that it will not be lost. How many sources are we talking about though? We're talking about 7 of them. Okay, 7 sources that we're trying to track. How does that 7 affect this? If I have 7 of these things to the 7th power, okay? But again, this is the probability of none of the 7 being lost, which is the exact opposite of what you actually want. What do we do? 1 minus. Perfect. Any question on those? On the at least one cases? All right. A recent census at a major university revealed that 40% of students mainly use Macs and the rest use PCs. At the time of the census, 67% of the school students were undergrads and the rest were graduate students. In the census, 23% respondents were graduate students who said they used PCs as their primary computer. Suppose we select a student at random among those who were part of the census. What is the probability that the selected student is a graduate student or uses a PC? All right. So, again, let me just ask you, what word kind of sticks out here? Or. All right. So what caught my attention is this word or, because or tells us to do what? Add, and then maybe, yes, for sure add, subtract if there's an overlap, okay? So we're going to have the probability of being a graduate student plus probability they use a PC minus the probability of graduate student and uses a PC, all right? That is what or means. Add with subtraction if there's an overlap, okay? And remember, the nice thing about this, isn't this in your AP formula packet, right? So you don't have to memorize that. You just have to know when to use it, and then you're free to look it up if you need to remember a piece of it, okay? Now, let's see if we have all the pieces that we need. Probability that someone is a graduate student. Okay, well, we're not straight out given that, but we're given something almost as good, right? So it tells us 67% are undergraduates. So what would that mean about graduate students? 33%, right? The ones who are not undergrads. Perfect. We need the probability a student uses a PC. Well, along similar lines, so we're not actually given that information, but we're given something just as good. What percent of students use PCs here? 60. And how do you know that? Yeah, because it says 40 use Mac, so the rest use PCs, so this would be the rest. Okay? Minus the probability someone is both. What's the probability someone is both? What? 0.23. Beautiful. Isn't that what this probability is right there? All right. So here we add all of this up, and I think you should get 0.7 when you do. Correct me if I'm wrong. Yeah? Perfect. So any questions on that? Because again, that formula is going to be important. You are going to need to know how to use that formula for your test. So any questions on part A? All right. Part B, suppose we select a student at random from among those who are part of the census and learn the student mainly uses a Mac. Find the probability this person is a graduate student. Show your work. All right. So, given that, where? Oh, okay. It doesn't say given that, but we're told the student mainly uses a Mac. So, again, in my mind, what I'm hearing is given that the student uses a Mac, what is the probability that they're a graduate student? Can everybody see how that translates to how I'm phrasing it, right? We know something about this kiddo now, right? We know that they use a Mac. Now, given that information, we want to know the probability they're a graduate student. It does matter, but also keep in mind this is what we were given. Given that they use a Mac. Yeah, the given goes second. So think of this bar. This bar here, think of that as the word given. Probability that they're a graduate student, given that they use a Mac. All right. Wait, actually, I think I might change this just so I don't confuse the crap out of you guys, because this way is actually a lot more challenging. Why don't you guys, just for your own sake of mind, change this to PC? That's actually going to be much, much easier for you and more similar to the rigor that I need. Asking about Mac would be much, much more complicated. So why don't we do it this way instead? Still same idea though, right? We know something about the kid, and now we want to know the probability of something else. Now there's a formula for that, isn't there? Right? Smile and nod. Give me something, guys. Yeah, there's a formula for that. All right, so let's recall how the formula works. So let me grab this for you really, really quickly. So in here, the formula is right here. So on the top of the third page, it says probability, and there's two formulas there for you. This is the second setup, okay? And what that setup says is this. Now, in my mind, that isn't really telling me very much, is it? So what did I always do? I didn't just start plugging in numbers. What did I do before I worried about the numbers? Instead of looking at this, what do I do with this? Uh-oh. I put this in context of my own question, right? I wrote it in the verbiage in the context of my question, okay? Again, just to help myself. So isn't the top the probability that both happen, right? So this is a probability someone is a grad student and uses a PC, right? That's what both would look like. Divided by the probability of B, well, look at B's placement. B is that the condition actually happened. In this case, what's the probability the condition actually happened? What is our condition? The PCs. So again, if I know I'm going to need that formula, I translate it into my context, the context of my own problem, to make it easier to maneuver, easier to use. Okay, so now going back and looking at the context, now I know the formula, I've written the formula out. What's the probability someone is a grad student and uses a PC? That's the first thing I need. What's that probability? 0.23. Probability that they use a PC. What's the probability that they use a PC again? 0.6, right? It was the opposite of this. And where did I set my calculator? 38333. Right, any questions on that one? You guys are really quiet. Is this just a case of the Mondays, or am I actually like boggling your minds this much? What? It's a Monday. All right. Tree diagrams can organize problems having more than two stages. The figure shows probabilities for a charity calling potential donors by telephone. Each person called is either a recent donor, a past donor, or a new prospect. At the next stage, the person called either does or does not pledge to contribute, with conditional probabilities that depend on the donor class the person belongs to. Finally, those who make a pledge either do or don't actually make a contribution. So our first question, what percent of calls result in a contribution? All right, well, I see three ways of ending up contributing, right? Can everybody see that? Right? Three ways that we can end up contributing. How do I find the probability of each one? How would I find the probability a recent donor makes a pledge and ends up contributing? Yeah, don't you just multiply down your branches, right? So for each one of these, so for the top one, 0.5 times 0.4 times 0.8, this top one has a 16% chance of happening. This middle one, 0.3 times 0.3 times 0.6, has a 5.4% chance of happening. Then this bottom track, 0.2, 0.1, 0.5, 0.01. So from my point of view, those are the three different ways we can end up with a contribution. Okay? Now, if it can happen this way, or this way, what do we do with those ors? This, or this, or this? Add them up. All right. Oh, sorry. And that gives us 0.224. So 22.4% chance that they end up contributing. All right. So, what percent of those who contribute are recent donors? All right. So, here we actually know something about the person that we're talking about. So here, what do we know about the person that we're talking about here? When we're talking about the percent who contribute, or what percent who contribute are recent donors, what do we already know about the person in this case? What? I'm actually confusing myself in this case. Yes. Yes. All right. So here for this setup, we already know that they're a donor, right? We want to know what proportion of them contribute. All right. Now, I will say, while the language can be wishy-washy in these, when it comes to the test, I specifically chose ones that are very obvious that they're this setup. Okay. It's not wishy-washy like this. It is very blatantly obvious. What word would make this blatantly obvious? Given, yeah. So here again, if you see the word given, you know to use this process. And again, I did make sure that my test is obvious in what you're supposed to be doing. Okay. So if you see given, that's this process. Okay. I know the language I've chosen can sometimes be a little wishy-washy, but if you see given, that's how you know for sure. So here, again, there's a formula for this, right? So make sure, again, my best advice for you in using that formula is translate the formula into words, okay? In your packet, you are going to see this. But again, I don't find that particularly helpful. I think it's more helpful to have it in context so you really know what you're supposed to be looking for. So here at the top is the probability that both happen, right? The probability that they're a donor and contribute divided by the probability that the condition ended up happening, that they actually are, or that they actually were a recent donor. So let's take a look at, so here they talk about a recent donor. Well, what's the probability that someone is a recent donor and contributed? 0.16. What's the probability someone is a recent donor? 0.5. Isn't that already in the table? There's only one branch to represent being a recent donor, and it's 0.5. It's half of them. And if I'm doing good mental math, I think that should be 0.32. Somebody correct me if I'm wrong. Yeah? Perfect. All right. C, what percent of calls were donors who ended up contributing? Isn't this actually the reverse of what I just asked? Now, I'm assuming, hey, given that the person contributed, what's the probability that they had been a recent donor? Okay. Actually, I just noticed that too. So it looks like here it could be both. So here, I should actually change that to recent, just to be more clear. So here, probability that they're a donor, given that they contributed. Okay, so given a person contributed, what's the probability that they were a donor? And again, I like that there is a distinction here. There's two different ways to be a donor, right? So this is an overall donor, past or recent, would qualify as being a donor here. The first one, they did specify we were only talking about recent donors. So, again, what's my best piece of advice? This is what your formula packet's going to tell you. What do I want you to do to clarify things for yourself? Write it in context, yeah. Write it in what makes sense to you according to this problem. So here, probability that someone is a donor and contributed divided by that the person actually contributed. All right. Now here again, thinking in general terms, right? In general terms, we're talking about a donor. So to be a donor and having given a contribution, aren't there two paths that lead to that? Right? Can everybody see that? In this tree diagram, there's two paths of someone being a donor and contributing. So what do we need to do with these if this or this both qualify for that? We need to add those together. Okay? We have two branches representing donors that are contributors. So here, 0.16 plus 0.054. The bottom, what proportion of people contributed? 0.224. Isn't that actually what we found in part A? Right, so do we need to recalculate that? No, you already found it. And again, the AP exam is notorious in probability questions for doing that. In some earlier calculation, that can help you with your future ones that they're asking you to do. All right? So if we calculate this out, 0.16 plus 0.054, then divide that by 0.224, 9554. So of the contributors, 95.54% of them were already donors, either recent or past. All right, any questions on that one? No, that one got a little bit sticky in the middle there. Any questions on how we ended up doing it? All right. Then what about ones like this? I know I've shown you this before too. Suppose that A and B are independent events with probability of A being 0.5, probability of B being 0.3. What is probability of A or B? So again, what I'm hoping catches your attention is that idea of or. Okay? Again, in formula, what does or mean? Add, but then maybe subtract, all right? So probability of A or B is going to be probability of A plus probability of B minus if there's an overlap, okay? Now, we're not told that there isn't one. So we have to assume there's an overlap here, right? We're not explicitly told there isn't one. So we have to, yeah.
Doesn't it say that they're independent events, though?
Yes, it does.
Does that mean that there is an overlap?
It means there is one, yeah.
Okay.
Yep. So, but the question is, how do we find that overlap? So I do like that independent drew your attention because it actually helps us find that overlap. Something and something else happening. If they're independent, what do we know? They do, and independent tells us we can what? Define and. Typically we think or meaning addition and meaning multiplying, okay? And the fact they're independent is what tells us, yes, we can actually do that. So the fact that this is independent tells us that this overlap is actually just the two multiplied together. That's what it means to be independent. You can just multiply. Yes. You couldn't. Nope. So that's why that's a very critical word here, because if they didn't include it, you actually wouldn't be able to solve this. Great question. So here we have, I'll do it in a different color. We have 0.5 plus 0.3 minus, what do we multiply those together? What? I think is it 0.65 total? Because that'd be 0.8 minus 0.15. Yeah. And do we still have more, or is that all?
Just one page.
No, we still have one more page. All right. But everything I do is good.
I want to do it.
Thank you. Thank you. Also, keep in mind, if I took a third day to do things for you, likely where do every one of these examples connect to somehow? To the test, right? I've chosen each of these for a very particular reason to make sure you re-see that skill before we get to the test. So the following are the national score distributions for a past year of AP Calc 1 and AP Calc 2 scores. Okay, Lauren took Calc AB and Jenna took Calc BC. What is the probability both get a 5 on their respective exams? All right, so we need Lauren to get a 5 and Jenna to get a 5. Okay, how do you find that? How do you find something and something else happening? Multiply. So to find the probability both of them get a 5, wouldn't that just be multiplying these two values together? Right? 0.19 plus or times 0.403. So that's the probability that they would both get 5s. Yes. What? Oh, yeah, that's a 3, sorry. All right. The following is a national score distribution for a past year of AP statistics. If students' scores are randomly selected, what's the probability that they receive the same passing score? All right. So let's think about this scenario. So first of all, what does it take to get a passing score on an AP exam? 3, 4, or 5, right? So these are the qualifying passing scores, right? And we're looking at taking two students, and we want them to have the same passing score. So aren't there a couple ways that could happen, right? They could both get 5s, couldn't they? Uh,
That's
uh,
not possible.
I've had kids get 5s before. It's very possible. Wouldn't that be both kids getting a 5? Right? Yeah. All right. Or couldn't both kids get a 4? Or couldn't both kids get a 3? Correct? Now notice, wasn't I using the word or in between each of these? This could happen, or this could happen, or this could happen. Oh, that is too many decimal places there. There we go. So again, notice my deliberate use of the word or. This or this or this could happen. What do you do between each of those ors? You add them. So this would be a formula of what you type into your calculator to figure out the probability of them getting the same passing score. All right, 1, 2, 8, 8. Any questions for me on that one? Anything at all? All right. 2 multiple choice, and then we will be done. So given that the probability of E is 0.25, probability of F is 0.34, and the probability that both happen is 0.085, which of the following is correct? All right. So here they're talking about independence versus mutually exclusive. All right. The easier one, okay, the easier one is mutually exclusive. All right. What does it mean to be mutually exclusive? It means they don't have an overlap. But what do we definitely see here? We definitely see an overlap, don't we? So because that and exists, that means there's no chance that they're mutually exclusive. right? So which options can I rule out right away, just knowing they cannot be mutually exclusive? Well, no, we need it to not be. So wouldn't that mean it can't be A? We know they're not mutually exclusive. We know it's not C. Here it says there's not enough information, but we had enough, right? We know for a fact they're not mutually exclusive. So right off the bat, can't we get down to a 50-50 shot here, right? Now let's recall independence, okay? Doesn't independence mean that one thing shouldn't have an impact on the other thing, right? So another way to phrase that, again, doesn't that mean the probability of E happening, if they actually are independent, should be the same as E happening, even if I know that F already did? If they're independent, shouldn't this be true? Is everyone with me on that? Yeah? I'm getting a lot of blank stares. Smile, nod, give me something, guys. Yeah? Okay, beautiful. So, what's the probability of E happening? Oh, 0.25. Well, that's easy. Probability of E given that F already happened. Isn't there a formula for that? Isn't this where our formula tells us it's a probability that both happen divided by the probability that the condition actually happened? So if I'm filling that in, wouldn't that be 0.085 divided by 0.34? And I need a calculator for that. And look at that. They're actually exactly the same. So they are independent. That knowledge of F happening had no impact on E happening. Okay, so they are in fact independent, which would make it D. All right, now. Oh, it's not going to let me move it. Dang. All right, now this next one. So pay very careful attention to this next one for me. All right, so this is relating the idea of mutually exclusive and independence. Okay, now let's start with mutually exclusive. Okay, if they are mutually exclusive, okay, then let's say we're talking about events A and B. If they're mutually exclusive, if A happens, does that tell me something about B? Yes, it does. What does it say about B? If they're mutually exclusive, A happens, what does that mean in B? It can't happen. All right? So, vice versa, let's say they're mutually exclusive. If A doesn't happen, doesn't that make it more likely for B to happen then? Right? So, what I'm hearing is when it's mutually exclusive, you are guaranteed to know something based on the other outcome, right? If they're mutually exclusive, knowing something about A most definitely tells you about B. So is it possible for something to be both mutually exclusive and independent? No, it's not. Because again, if they're mutually exclusive, you are guaranteed knowledge of the other outcome. Does that make sense to everybody? Yeah? So which one fits that idea that they cannot be both? No, C is the opposite. It says if they're not mutually exclusive, they must be. Oh no, I'm sorry, not opposite, but it doesn't guarantee you not one than the other. It's E. Yep. So if they're independent, they cannot be mutually exclusive. It cannot be both together. Okay. So again, do please pay careful attention to that one, because I do find that a very interesting problem that it cannot be both. And I think that's it for today, right? Oh, thank goodness. Oh, sorry. The probability that at least one is defective. So at least one sticks out to me, right? Because what's easier to calculate rather than at least one? helps, like having just an extra day to sort all this out. Yeah. Because following the books and stuff, like they go through chapter 5 way too fast. Like, no, kids need time to process all this.
The other day.
Oh, perfect. Thank you.
Do you watch it?